good morning, everyone. So we are in the third class of the structural dynamics lecture. So we have completed up to today. We have completed the single degree freedom system, free vibration for damped, undamped case, and then we extend the concept for the damped structure. So now, and we have seen few things. For example, if I go back quickly. So we have seen that how we can able to derive the how we can start making a mathematical model of any complicated structure into the simplified mathematical form in terms of differential equations. Then we can see that how we can able to solve that, like how we so that thing we have seen, how to implement the initial condition that we have seen. Then we have also seen that how to incorporate the damping into the calculations, and again solve that. We have also seen the differences between the over damped, under damped, and critically damped structure, and we have also seen that how those responses are coming into picture. We have also seen that how we can able to see the response using the MATLAB software. Okay, so now from here let's start discussing that how how much energy is associated with this type of systems. Because what we have seen, we mostly focused on the response of the system, that how the structure is going to vibrate. So we mostly seen how much displacement it occurs, how the displacement is varying with the time, and we have also seen how the velocity of the system changed. We have also seen the displacement versus velocity plot. So if I just started putting one after another, then first thing is that we seen that with time. So if I just put it time here, so how the displacement is changing, maybe how the velocity is changing, that we have seen. And we have also seen that how the velocity, displacement versus velocity is changing for a system. So this plot is known as phase portrait. The phase portrait. Okay, so in the phase portrait, so using the phase portrait, we can see that how the structure is like oscillating and how its velocity and displacement get changed. So we see that once the structure is in the undamped situation, in that case these become like a circle, single circle. That circle will no longer like get condensed. But once we are solving any damped situation, in that case what will happen? This circle starts spiraling towards the center, and eventually it goes to the 0, 0. Okay, so if we see that the black line is the damped case and is undamped case, and the red line is the damped case, then what is the prime difference between these two? You may say the presence of damping. Now if you think the presence of damping, how it is actually affecting, it is dissipating the energy over the oscillations. So that is the only change in that two system. Okay, so now, and therefore what is happening, a circle is condensing to a spiral, and it is traveling from one position to another position, means one position to the 0, 0, that is a rest position. Okay, so we first try to think the two important aspects of it, that what the phase portraits actually means to us. Because we see that, okay, this is the plot between the displacement and velocity. Fantastic, that is true. But does it tell anything beyond that? So if we try to think that, what is our equations? So we have the equation of single degree freedom system is mx double dot plus kx, that is equal to force, or it can be 0, so forced, for F for forced, and this is for free vibration case. Okay, so we were discussing the free vibration. We have not go into the forced vibration yet. So this is our discussion point. So now if you see that here how these terms are actually affecting. So mx double dot is the inertial term. So you try to move that system and it start giving the inertia. For example, we are sitting in the bus start, we feel a back push on that, and so that is the mx double dot. And what is kx? Kx is the restoring force. Like for example, you compress the spring, therefore the spring start giving you a force. Or in this case, like once you are going that side, so you are pulling that spring, therefore the spring is pulling you also in the opposite direction. So that's the restoring force. Now if we try to understand how much energy is associated with that, can we able to do that? So for example, so if I see that what is the restoring force, so restoring force is my kx, and if you see that kx is a non-dissipative conventional type of force, because this force is not, I mean, this due to action of this force no energy is get dissipated. So this is a conservative field. If I say in terms of the physics, it's a conservative field. If I do some work, the work will be stored into that system. It will not going to lose it. Do you remember the conservative field? If anybody forget, please get it clarified. Like for example, if we are doing some work against the gravity, it's a conservative field. It stores the energy. If we lift something, it stores the energy is stored. Then it, if once we release, it will come back. Here the spring system is also something similar. If we stretch it or if we compress it, it will stores the energy. Okay, so restoring force is kx. So now, so if I try to see that we have a system like this, and now we extend it by a x amount, so it gives you a force. So that force is the kx. Okay, so how much work we need to perform to move it? So you can see that if we are displacing it by the x amount, it will have a force of kx amount. So how much energy we have to perform? Means how much energy is required to displace it some amount. So if we try to first plot that this is my x, then this is my force. How much force is required? That is kx amount. So it will be a straight line. Perfect. So force will be kx once we have a displacement x. Then, so now energy or the work done, energy required or the work done is the area under that curve. So we can simply calculate the area under the curve is kx into x. So that will be half of k x square. Or we can do that from the integration as well. We can say that at the x distance the force is kx. Okay, so if I just do that, so in work done or the energy required equal to kx amount, so for dx movement, and we are just integrating it from maybe from 0 to x length. So it will become half of kx square 0 to x, so half of kx square. Okay, so that much of energy will be stored into it. Now think, one of the most important point is that we are giving some initial condition. Okay, so before we go there, so that is the energy required or the energy stored. So this energy stored as a elastic potential energy, or we can say that this is a, sorry, yeah, so that is like as like a potential energy. This is stored as potential energy. Okay, we get that energy as a potential energy. So if we have some velocity, how much kinetic energy will be stored? So kinetic energy will be half of m into v square. What will be the kinetic energy? We all know that. So that will be so we get that two thing. So now if you see that the phase portrait starts from which point? At the initial condition. So it starts from the initial condition, because suppose whether it is damped or undamped, because undamped case we cannot able to identify that from where it starts, because it's just a circle. So it's a from where it starts is difficult to say. Yeah, we can see the code and we can tell that okay, this point it starts, but if we just see the phase portrait, it's very difficult to say that from where it starts. And but for a damped system, we can able to understand whichever is the farthest point, it will start from there and it's coming back. So maybe we can see that okay, this point is the point from where it starts. So this point, that initial point, will be associated with some sort of energy state. Do you agree with my statement? Agreed? How? Because that state has some type of initial velocity and some type of initial displacement. Now once you have, so let's just put that initial displacement is maybe x0 and initial velocity is x0 dot. Okay, so how much is the potential energy? So potential energy will be half of k x0 square, and kinetic energy will be half of m x0 dot square. Make sense? Everybody agreed with me? Agreed? Very good. So my total energy is how much? Half of k x0 square plus half of m x0 dot square. So that is my total energy for that system. Okay. Now here, one of the most important thing you can notice. So suppose, okay, just let's do one or two step more from there. So now let's see if we are discussing about a SDOF system with undamped friction, undamped SDOF. So in that case, what is my solution? X equal to, anybody? We can also go back and we can check what is our solution. Yeah, that was my solution. Xt equal to x0 cos omega t plus x0 dot by omega sin omega t. Very good. So x equal to x0 cos omega t plus x0 dot by omega sin omega t. Am I right? Okay. Am I right or? Yeah. Good. Perfect. Okay. So that was my solution. Okay. So now if I start thinking that total energy, how it going to change? So if I try to see that total energy will be half of x square kx square plus half of m not x0 what I should do, I should take the m out. Wait a minute. half of k x square plus half of m x naught square, not x not 0, no, that's the thing. Okay, so then we can have equal to half of m. If I just take m as common, and what will be the x dot from here? So x dot will be equal to I omega times x, or not I omega, or that I can write x dot will be equal to omega x0 sine omega t with a minus sign plus x0 cos omega t. I should write that. Very good. So if I just take m as a common, so I will have omega square into x square, that is x0 cos omega t plus x0 dot by omega sine omega t. Use that half here, unnecessary, whole square plus minus omega x0 sine omega t plus x0 dot cos omega t whole square. Okay, agreed. Okay, so if you are agreed, I can do one thing. I can take that omega square and I can just put it inside as this and take this one. I can do that. Simple, I just take it inside. So half, then it will become omega square x0 square cos square omega t plus 2 omega x0 dot sine omega t into cos omega t plus x0 dot square sine square omega t. I'm just expanding a plus b whole square, nothing else. Okay, and this one will become omega square x0 square sine square omega t minus 2 omega x0 sine omega t into cos omega t. There will be another x0 dot plus x0 dot square cos square omega t. Okay, these are the two terms. If I just expand that thing, everybody agreed with me or I made some mistake? Okay, I did correctly. Good, noise. So what I can see, these two terms can be cancelled out. They are just plus minus. So what I left with? I left with half of m into omega square x naught square plus this much. And if I see the total energy here, half of m, I just taking m common, so I left with omega square x0 square plus so we can see that the total energy at any point over the time and the total energy from the initial condition are exactly equal. That term wise equal, so there is no need to plot or show. All the terms are same, so they will be definitely be same. Okay, so why is that? Is it correct or it is something wrong thing came? Exactly, the dissipation is not there, so the system is conserving its total energy. It is maybe converting from kinetic to potential and potential to kinetic. That is all right, but the total energy is conserved into the system. Okay, so therefore we are getting the total energy conserved. Okay, now this tells another very interesting points in our mind. That is, once we are looking at the phase portrait, we see for a undamped case, the phase portrait is nothing but a circle or ellipse, but it's a closed loop system. It is not like a open-ended spiral type thing. Okay, so in that closed loop, now if I change the initial condition, and the energy is function of the initial condition. If you see that energy is the function of the system property and the initial condition, that is function of x naught and x naught 0. Sorry, x naught means x dot naught. Okay, that which is the initial velocity and initial displacement. So once we are having that energy is the function of this, and the phase portrait is dependent on the initial condition, then we can say that phase portrait, one closed loop, is dependent on the energy. So if I change the initial condition, definitely it will start making the different phase portrait. And these different phase portraits are associated to the particular energy state. Do you agree with my point? And once the system is undamped, it will just oscillates in that phase portrait only. It cannot able to go out from that line. Make sense? All of you agree with me? Any disagreement? Anywhere, any confusion? Please feel free. Everybody okay? Perfect. So, what else we can able to thought from it? Now, that also tells 2-3 very interesting point. That once we have that phase portrait, can we also able to calculate the natural frequency from the phase portrait? Because now the phase portrait gives a more intuitive idea about a free vibration. Why I am saying a very intuitive idea? Because if you see, what is the time period for a vibration? Can we see it from the phase portrait? We can see that. Like for example, it starts from here, this point. Once it goes and completes this circle, that is the time period. The time taken for completing one loop in the phase portrait is the time period. Agreed? And this shows a particular energy contour. Now let's see what happened and how it is associated with the energy profile of the system. So let's see that. So if I say that potential energy is half k x square. Okay, so how it should look like? If I try to plot the energy here, and here if I put the displacement, how it should look like? It's a parabola. Exactly. And that 0 point, the zero displacement, actually represents the mean point. So if I just think that my spring mass system, so maybe that point is the where it is in rest, then it can go here and it can go here, so it can oscillate between these 2 points. Okay, now once I am actually giving some type of initial condition, that means I am displacing it here and the potential energy is increased here, then the system is moved with that well. Agreed with me? Okay, and you can see that y-axis is the energy function. So once it moving up, it actually storing its energy. That is also evident from that, like half of k x dot square is the stored potential energy for that system. Make sense? So that is the initially stored energy in that. Now once we leave that system, how intuitively it will work? Just forget all the structural dynamics and anything. Just you have like a system like that, you put the ball here and you leave it. How it will oscillate? Yeah, it will should come, go, come again, do like this way. And how long it will go? It will go up to here. If the system does not have any damping, agreed with me? It will go and come back. And we can see that half of kx square is a potential energy function which is symmetric about the y equal to x equal to 0. So it's symmetric about this line x equal to 0. It is symmetric both the side. So whatever the distance it goes here, it will go here also the same distance with the same amount of energy. It will dissipate and it will go and it will oscillate in this way. Make sense? And the time from here to here is the half of the time period. Going from here to here is a half of time period, and once it come back, it's a full time period. So can I calculate the time period from very intuitive manner? Anybody? Let's see how we can do that. So half of m into v square, that should be equal to total energy minus potential energy. Okay, so total energy is how much? Whatever the energy we have given. So here, once we are leaving that ball from this point, we should understand in the phase portrait how it should look like. We try to draw the phase portrait just below it. So this point we are starting, or maybe this point we are starting. So we are starting from where the velocity is equal to 0. Okay, because we just take that ball up and we let it go. Please remember, in this representation, the velocity axis is not seen. We can just only see the displacement axis. Velocity axis we cannot see. That is maybe inside, but I did not draw the 3D shape of it. I just draw the 2D shape. So please don't consider that portion. Okay, just leave that. So we can just, and as we see that in this phase portrait, all it is associated to the energy. So all the points of that loop should have the same energy. We have also shown that. So we can start it from any point. It should represent the same energy. Okay, but I'm not going into the displacement velocity side. I am just taking only the displacement point. So please consider that velocity is equal to 0 at that point. So whatever the displacement is required, we should start from there. Okay, agreed? Very good. So now if we think that what is the E value, E will be half of k x0 square minus potential energy will be half of k x square. Okay, please pay attention, that is x0 and this is x. So it's a constant value, it is varying with time. Okay, and this will be half of m. V is yeah. Okay, so let me just do that. So that will be v square will be equal to k x0 square minus x square. I just take this common and half is cancelled with this half and divided by m. Okay, so this will become omega square x0 square this. Okay. Now what is v? Velocity, that is dx over dt. Okay, and x is x. Okay, no issue. So if I do that, v equal to omega times root over of x0 square x square, I can write it. Here I should put dx over dt, this. Any doubt? Very good. So now think, pay very good attention on that. Now I am trying to doing the integration from one side to other side. Okay, so I have to integrate the full system. Make sense? So I should write it this way, that dx dt, that is difficult to write in this form. So what can I do? I have the x here and t here, and I try to find out the t. So can I do this way? Can I write this way? Do that? Very good. If I write this way, what will be the limits for my integration? Think that once the ball is here, its amplitude will be x naught. Very good. So I just put x naught here. What is the time? 0. Put 0 here. Make sense? Okay. Once it goes from here to here, what will be its displacement? Minus x naught. Very good. What will be its time? T by 2. Exactly. Okay. Can we do that integral? Now if we just solve the integral, so now if I think, if we just try that left hand side, the right hand side, I just try to make it in the left hand side. So that will be t by 2. Okay. So what will be the right hand side? Integral of x0 to minus x0 dx omega x0 square by x. What is the integral for that? Sine inverse of x naught. Where is omega? Omega is out, maybe. Yeah, this is the case. So now if I try to substitute it, we will have t by 2 x naught by omega and this. So sine inverse of this. So if I just put sine inverse, first one will be minus x naught by x naught minus sine inverse x naught by x naught. So that will be x naught by omega into sine inverse of minus 1 minus sine inverse of 1. So what is the meaning of sine inverse of minus 1 and what is the meaning of sine inverse of 1? Huh? Yes, so first one is the minus pi by 2 and second one is the pi by 2. So I'm just taking it from here, this side. So my t by 2 will be equal to x naught by omega, then this is pi by 2 or minus pi by 2 minus pi by 2. So x naught by omega into pi with the minus sign. So I wrote that. Then, and also one thing, maybe I just put w. Just assume that w is omega, a is x naught and x is x. Okay, so I have to perform the integration. So I will just write int, then int is the a for integration, and you can see that once you are doing the MATLAB, it is automatically showing you how to write it. So it's wrote expression comma variable, comma name, comma values. Okay, so here I can just put what is my expression, that is 1 divided by W into sqrt a square minus x square okay, comma x. Okay, so if I just give that, let's see. So that is the output which is showing the integral of root over of 1 by dx into root over of a square minus this. If we are doing the integration, that will be the outcome. That. So a tan, that is tan inverse, not at all sine inverse. You see, whatever MATLAB is giving, that is tan inverse. They are telling that tan inverse of x divided by root over of a square minus x square. So tan inverse, that is also sine inverse. That is also true. So maybe in this case we can do one thing. Simplify. Sometimes this type of thing happens. So in those cases we can do simplification. That is not happening. So we can also need to put assume a no, wait a minute, something. That's you see that it is giving a general form of, means it was giving the general form of the solution. Now once I tell the computer that now assume that a is a real number, then it gives that okay, it is the sign. So I get a, so w is my omega, a is x naught, so x naught into sine inverse, sorry, that is not a, no, that is a sine, that is sine inverse a by this divided by omega. Okay, I got that. So 1 by omega sine inverse this, that is correct, 1 by omega sine inverse this much, nothing else. Okay, and I think this also shows that how to do that in MATLAB, that if you are stuck with this, you have a very powerful beast. You just have to know how to use that. Okay, so all the integration and all those things it can able to perform very nicely. Perfect. So we have that. So now just forget this x0 here. ये इधर भी काम नहीं कर रहा है, so forget that. Okay, so we can get this value. So we can say that t equal to 2 pi by omega. So that is my total time taken for this, and you can see that that is the value of t, the time period, that is nothing but 2 pi by omega. So this also provides you a very nice way of, so the more important point is where that once we are having like a circular loop, and if we perform the integration over it, we can also able to trace what is the time period of that system, that we can able to find it out. This technique maybe is not that much appreciable for the linear this type of systems, but once you will encounter something very tricky type of potential energy function, then this method is a very, very helpful thing. For example, if instead of the kx square, if I just say that you have a spring force which is something like your elastic force function is is k1 into x plus k3 into x cube, which is nothing but a Duffing oscillator, then calculating the time period will not be that easy directly. Then this is one of the method by which we can able to calculate what is the time period. And in those nonlinear cases, because this is a nonlinear case, it is not a linear case. Once we have solved this Duffing oscillator, it's a nonlinear oscillator. So in those cases, your solution will start becoming amplitude dependent. So your natural frequency will no longer a constant value. It becomes it depends on the amplitude. So for example, this circle has the time period. This circle also has the same time period. Once the system is a linear system. Okay, these circles may be different. They may have different energy state. But the important point is that whatever the energy states they have, they all are having the same time period. Because time period is just only 2 pi by omega. That does not associated with what is the initial condition or what is the initial energy is associated with that. But that case will no longer remain valid for the nonlinear dynamics case. Once you will start solving the nonlinear cases, this phase portrait will be associated with the different energy state, and their time period also will be different. They will be no longer same. Okay, so I just introduced that concept, although that is not the part of this course curriculum at all. But if anybody is going to do some research on the nonlinear dynamics, then please keep that thing in your mind, that there the natural frequency will no longer remain constant, and they are associated with the phase portraits, and phase portraits are always like showing the energy, but those phase portraits will also result different time periods. Does that make sense? One simple graph can tell so many things. Okay, after this is clear. Any question? Any question? Anyone? Okay. Okay, so if there is no question, then we can go ahead further. Yes, so we have seen already that, okay, so now maybe I can quickly show you guys that how the energy is getting changed. Okay, so let's run that one. Maybe I just enter like a 10 mass 1. Damping, let's first put it 0, so that undamped case. Initial displacement, maybe I will put 0.1. Initial velocity, maybe put 0.1. So that is the graph from the last class we have discussed. So you can see that. You can also see that phase portrait is like a exactly circular type of phase portrait. This thing goes like, yeah. Now this is the new plot. So here you see the blue line shows the, so this is the phase portrait plot, the right hand side one. This is the phase portrait plot, and this plot is the 3 different energy plot. Okay, the blue one is the kinetic energy, and the red one is the potential energy, and the green one is the total energy. Okay, so what can we see? That green line remain constant. You see the green line? Can you see the green line? So at top, that green line remain constant. It is not changing at all with time. Okay, but your red and blue lines are just like k sinusoidal motion, but they are not going below zero. Why? It's energy, it cannot be negative. So it is always above zero and they are oscillating. So therefore we are getting a constant graph at the top. What we have also discussed in the full discussion, that yeah, the energy will remain constant. Now obviously if we are putting some damping, then what will be expected thing? It will be decaying. So let's see. We already have the code because that code is written for the damped system. Now just need to put some damping value to be able to have that. Okay. So now again I will run that. So maybe I'll just put 10, 1. Yeah, now here I may be putting it 0.5 maybe. Little bit less, 2.2. Initial resolution 0.1. 0.1. Under damped, very good. Nice. Under damped system looks very good. Was that expected? No? Not expected? Okay. So was it expected? First question. Expected, yes. Because you can think that, like maybe I will start from the phase portrait first, then I will go to the energy. So here you can see that it starts from a particular energy state. It goes slowly and it's getting decayed. What we have discussed already, that each circles in the phase portrait represents the energy. So once it start coiling down, that means it's losing its energy. That's why it is coiling it down. And that same thing we can see here also, that it starts from the energy state. You see the green curve, that is slowly decaying. So as many the cycles are moving, it is constantly losing its energy. So obviously the energy state at the very end state means like for example this point associated to the very less energy, and that we can see here, that is very less energy state. So as long as we are revolving, it start losing its energy. Any doubt in that? Good. Here also you can see that how it is square. So yeah, that we have discussed in the last classes. Very good. So suppose, can you able to see some sort of overdamped system? Critical damping is 6.3. Okay. So maybe if I just try to do some overdamped, maybe I will put the 7. 1. Critical damping I am putting 7. Initial displacement 0.1. 0.1. So you can see that the way full thing happened, maybe I just this is the so you can see like in the zoomed version that how it looks like. So it starts, then try to oscillate but cannot do much thing, and it get full decay. So first thing, the blue curve is the potential energy graph. So it is shifting from that point. So therefore the potential energy was very high. it gets reducing, and then it also has some sort of small velocity, and it get also decayed. So this way the complete thing is getting decayed. It almost become like a zero, there all the energy is lost. But in the last case, you see that there is some energy still remained in the system because it was keep continuing to the oscillating. But here full energy is gone. Good. Okay, so anything, any doubt in this regard? Is that thing getting cleared? Correct. Perfect. Because that type of detailed discussion on the phase portrait may be not there in any book properly, because these type of things are like not very commonly given in the textbook. So yeah, perfect. So we completed that portion, and now maybe we conclude with this the free vibration part. Now let's move on to the forced vibration, and let's see how the forced vibration part is actually occurring. So here today, if we see, we primarily discusses that how a system is oscillating, means how we can able to draw the phase portrait, what is the inner meaning of the phase portrait, what are the underlying things we can able to understand from the phase portrait, and how we can able to calculate the time period of a system from its potential energy function. And also, like for the linear case we see, and we have seen that that is not dependent on the initial condition wherever it is starting. But for case of the nonlinear vibration case, that would be something very tricky, and that is one of the very useful method for the nonlinear dynamics case. Perfect. So with this we are stopping the pre-vibration portion, and we are moving on to the forced vibration part. Perfect. So let's see in the forced vibration. So our equation of motion will be mx double dot plus cx dot plus kx, that will be equal to force. Okay. Within the forced vibration, previous case we have seen that we displace the system from its equilibrium and we let it go. So whatever the changes happened, it get die out after a certain time, and again the system become in its own state. Okay, but forced vibration is like displacing the system from its position, but you are keep applying that force so that it get displaced, and now it will be in that displaced situation. Okay, and then we try to see that how the system is going to respond on that. I generally give a very example. I mean, like one of the, I mean, I try to give an example from the real life for to understand the situation much better manner. Like for example, you were in the home, and then you somehow shift, like went to someone's house. Okay, so for the time being, it become like you have changed your state. So and then again you come back to your home, not a problem. So there is a just certain time of vibration or responses happened that get time out, not a big deal. But you can think the forced vibration is something like you came from your home to hostel. Now that hostel simulation start simulating you, and your habits get changed slowly. So you can see a long-term effect of changing of your systems. So you are no longer remain like a previously systems. Your natural frequency or your response is not your natural responses. It become like a more forced response or the forced vibration type thing. So there, like a forces try, that system will act according to the force. For example, like suppose you are about to go for bed around 10 p.m. but after coming to hostel, maybe you are going for bed around like a 4 a.m. most of the cases. so so how that change happened? That's the forced vibration. You can think in the real life because you are forced due to the hostel that okay, you changed your systems. So that type of thing is generally happen. And if you think it that way, you can also able to get a perspective on the real life, how the dynamics is worked. Okay, so you can try to put some equation for that, also modeling this thing. Why not? Why not? You maybe get the similar type of graphs out of it. Okay, so yeah. So now if we try to see that, so that's the first term is coming here. So once the fourth term comes into picture, where is the first change? Because previously the equation was homogeneous. Now the equation is not always homogeneous. Means now the equation is not homogeneous. It becomes heterogeneous equation. And it highly dependent on what type of forces you are applying. Because as I mentioned, that forces will try to make the system respond according to the force. Like your hostel lights, friends will not let you sleep at 10 p.m. That's not the case. That's not the case. So whatever is your natural thing, forget it. It will start stimulating you. So force vibration will let you go into that range. Okay. So in that case, so obviously you can understand that it has a very significant impact on that. So that's why it's also taught as a separate thing with the like a free vibration then force vibration. So first, like if I see that force is like a harmonic force, that is the very easy way to start with that. Okay, it's a harmonic force. So we are applying some harmonic force. So maybe I will just assume F into F e to the power I omega t, where omega maybe I'll just put it as a omega bar, so that bar is showing that excitation frequency. Okay, so now let's see if I have this way, and we have already seen that previous cases that x can be represented as x can be represented as x into e to the power of lambda t, and we had seen that these lambda, so we represented in this way that x equal to e to the power of lambda t for the free vibration cases, and we try to calculate what is the value of lambda. Agreed? And we saw that lambda comes plus minus I omega, where omega is nothing but root over of k by m. Okay, but that is the natural system's property, but you are no longer in the system range, now you are in the forced range. So you should not expect that the structure or system will oscillate in this frequency. That will not happen. That will not happen. The system will start oscillating in this frequency, omega bar, which is the excitation frequency coming from the environment. Okay, that frequency it will start oscillating, but it will take also some time to get adjusted. I will also again come into that, like how it will happening, all those things. So let's see. So if so first of all, this equation is a heterogeneous equation. So how we are solving any heterogeneous equation? What is the procedure of solving a or maybe non-homogeneous differential equation? We separate it into the two parts. One is the particular integral and another is the complementary part of it. So heterogeneous equation solution is the two part. So let me put it that way, that the particular integral and complementary part. Very good. So what is the complementary part? Complementary part is the homogeneous version of it. So complementary part will be nothing but mx double dot plus cx dot plus kx, that is equal to 0. That is the complementary part. And what is the particular part? Particular part will be mx double dot plus cx dot plus kx, that is equal to your force. That the force vibration part is the particular part. Now you can see that in the complementary part there is no force, so system will oscillate in its own natural frequency. Simple. So here if I try to get the solution, so I will get the solution like a complementary. I just writing xc, because my solution will be total xc plus xp, that will be xp, this will be xc. So complementary part is xc, into particular part is xp. So my total solution x equal to xc plus xp. Okay, makes sense? So here the system will try to oscillate in its own natural frequency. So what will be the solution? We already know the solution. We have done that in the previous classes. That is e to the power of minus xi omega t into a cos omega dt plus b sin omega dt. I am not writing that original like that x0 x0 form. We can do that and we can place that, not a problem. Yeah, this is the underdamped system. Yeah, most of the cases the life is the underdamped system. Overdamped system and all those things are quite difficult to get. Means we are not encountered that often. Now what happened with the particular part? Okay, so particular part is that the system will oscillate in the forced vibration manner. So here I should assume xp will be equal to x into e to the power of I omega bar t. And here I assumed, once I solved it, I assumed x into, maybe I should write it something, a into e to the power of I lambda t. So please pay attention that assumption of these two are different. Make sense? Because the responses are different. We know that they will be different. So we should solve it accordingly. Make sense? So once we are solving the particular part, we should assume it with the forced natural frequency, it is going to oscillate. So xp equal to x into e to the power of I omega bar t. So once this is the case, I omega bar t, so now we are substituting this one here. So this will become omega square m plus I omega bar c plus k equal to f0. If you think, there will be a, sorry, that with the x equal to f0. Okay, so there e to the power of I omega bar t here, and there is also this one, that two term get cancelled out. So we will left with this thing. Okay, so what will be my xp? So xp, amplitude of xp will be f0 divided by omega bar square m plus k plus I omega bar c. Okay, makes sense? Can I write f0 by k divided by omega bar square by omega square plus 1 plus I omega bar c divided by m into m divided by k? Yeah. What I did, I take the k common from the numerator, sorry, denominator. Okay, if I take the k common and put the k here, it's all right, not a problem. And if I take the k common, then what will happen? This k become 1 here. Okay, then minus omega square, and m is k by k equal to m omega square, that omega, the system's property. Okay, and then I omega bar then C I just divide by capital M and then multiply by M and divide by K, because K I have already taken the common, so K will be there, that 1 by K. So now if I see, how can I write it? F0 by K 1 minus, I'm just putting it as a eta bar square. So I'm just saying omega bar by omega equal to eta bar. That is the excitation frequency ratio. Okay, ratio of the excitation with your natural frequency, means the excitation frequency divided your natural frequency. Okay, plus I omega bar C by M equal to nothing but C equal to how much? Cc equal to 2 omega M, and C by Cc will be equal to xi. So C equal to 2 xi omega M, and K by M equal to M by K equal to omega square. Is it this? Yeah. So C by M equal to 2 xi omega, 2 xi omega into omega. No, but divided by omega square. Divided by omega square. So 1 omega get cancel out, and I can write it F0 by K 1 minus eta bar square plus 2I xi eta bar. Look, there is a 1 omega bar by omega, this remained. Okay, so I can able to write it in this form. Make sense? Please, any doubt, please feel free. No, not whole square, sorry. Thank you, yeah. It should not be whole square, perfect. Yeah, it should not be whole square. Any doubt up to that? No doubt, very good. So, this is my system. Now, let's try to understand what we get here. Okay, so what is F0 by K? K is the stiffness, F is the force. So force by stiffness, that means static displacement. So I can see that if I forget all those things, mx double dot plus cx dot plus kx equal to force, instead of those things, if I just simply say that I have a spring of K, and if I apply a force F on that, I will have a displacement F by K. Simple. So you can see that this is nothing but that one, which is the static deflection of that full thing. If I just apply a force very slowly, which ignores my damping dissipation as well as my inertial changes, I should get this one. Any doubt up to that? Very good. So if now that term get changed due to the effect of inertia and the effect of damping, and this is the effect of changes. Can I say that way? So this factor, which is nothing but 1 by 1 minus eta square plus 2I xi eta, that factor is known as dynamic amplification factor. So in the caudal profession also, you may have seen some of the cases, once we are considering the dynamic force, we increase the static force by some factor, and that is the logic that why we are increasing the force by some factor, because if you increase that force by some factor, this will suffice the full thing. Your forced vibration or the vibration due to the particular integral part you can able to get that. And we will also see that why only the particular part is the most important thing, not the complementary part. I will also come into that point soon. So this thing we have get. Makes sense? What is the dynamic application factor? And now you see there is also one tricky point in the dynamic application factor still there. That is, it's a complex number. If you see, the term is 1 minus eta square plus 2 into I into xi into eta bar. So that I is nothing but root over of minus 1. So how can we deal with that? Because we cannot able to understand what is a complex number in the real life. A number is number, but okay, now if it become a complex, come on. How we can able to understand that point? So that's a big challenge. So therefore, what we do, we try to get rid of it and we try to normalize it. So how we can normalize that whole thing? We generally do this way, that we will just multiply with its complementary part. This portion will become okay. So that is the condition. Am I right? No. The root will not come. I think this is the correct one. Okay. With the so now you see we are having this type of terms, and we can see that in this thing what is happening, that there is this term. I mean, I can say that this may be my denominator, maybe I can say r. So I can say that this is divided by r minus 2 xi this divided by r. That type of term is happening. Okay. So one part is the real and another part is the complex or the imaginary. So what is the meaning of it? So let me go most little bit. So if you see, we are having the equation like this. Okay. Okay. So once we are substituting xp equal to small xp equal to capital XP e to the power of I omega bar t, then xp dot is I omega bar xp e to the power of I omega bar t, which is nothing but I omega bar into small xp. And what is xp double dot? Xp double dot is minus omega square into xp. So that means if I try to draw the Argand plane, I think all of you know what is Argand plane. Argand plane is the plotting a plane where we plot the complex numbers. Okay. So I can see that the real axis is associated to the xp. This axis is associated to the xp dot, and this is associated to the xp double dot. Make sense? Any problem, anything comes in your mind, please feel free. Because these portions maybe you have not studied in your BTech level. I don't think so. If somebody teach that, fantastic. But so what is exactly happening? So now this full thing, if I just try to multiply those, like m into xp, c into xp dot, and k into k into xp, c into xp dot, and m into xp double dot, I can get some sort of vectorical representation. For example, if I just do it, that is my form of k into xp, this is my form of c into xp dot, and this is my vector for m into xp double dot. So these three vectors gives me a combined vector, and that is the resultant vector is mxp double dot plus cxp dot plus kxp. So once I am dividing that force with that vector, I can able to get what is the displacement out from that. Get that point? In the previous case, once we are dealing with only the stiffness, what we were doing? We were having only this xp. Only we have this one for the static case. We just have force divided by kxp. We will get what is the value of xp. Now instead of having it in a single axis, we are having that in the plane, and it gets shifted due to the phase also. So these complex numbers, what we are looking here, they are representation of the phase. They are representation of the phase. So once we are multiplying with the I, that means it is in the 90-degree phase. Okay. So if we are multiplying I in a displacement value, that means it is actually showing in the velocity. And once it is like a negative, that means it is in the acceleration. Because of this nice formulation, xp equal to this, and then xp dot equal to I omega into this, and xp double dot equal to this minus omega square of this one. So that is the point why it gets changed. So now we can think that this gets shifted, fantastic, but this also have its magnitude. Okay, so how much is the shift here? If I just go back, 1 minus eta square minus, okay, perfect. So if I just put it, 1 minus eta square minus 2i xi eta divided by 1 minus eta square whole square, but 4 square eta square. That was my term. So if I see 1 is here, 1 minus eta square is someone here, and 2 xi eta is somewhere in that. So that is my I axis, this is my 1 axis, minus 1 and minus I. Oh, which means you can also say that it should not be here, it can be here also. So where is that vector? So that vector will be somewhere. So first we have to reduce it. So this one will become 1 minus eta square. Perfect. And we will have this vector like this. That will be 1 minus eta square minus 2i xi eta, and full thing is divided by r. That means we are scaling it up, and means the bigger or larger. Means if you are multiplying a vector with some number or dividing, multiplication and division are nothing but the opposite of it. So if we do that, so it's like a scaling up and down. So we will see that how this thing is scaled thing, and you have the force. So if you so you can also able to calculate what is the magnitude of it. And what is the magnitude coming from here? The magnitude will be 1 minus eta square whole square plus 4 under root, and it is divided by okay. So what is the answer? So this factor is actually known as the dynamic amplification factor because previous one has some complex number, and as I mentioned, we cannot deal in our real problem with a complex number, and these actually make more sense because this tells what is the magnitude of the force. So that magnitude, if you think, means you have a circle. So whatever the direction the velocity displacements are placing doesn't matter, but they will not go out from that. So that's why in the dynamic amplification factor, we are considering the magnitude like this, magnitude of that complex number. Thank you very much.